Hello. These are a few of my favourite things was supposed to have been the title of my talk at the 2020 conference of the Mathematical Association, which is a lovely occasion where maths teachers shared their ideas. The conference was cancelled, so I decided to make some videos about some of my ideas, which are about questions my students most often ask. And we start with, why does the graph go left when you add one to its input? So we're talking graph transformations. And it turns out there's a lovely way to explain that uses the idea of mappings. Well, we start with functions, so let me just hide myself. We're talking about real functions of a real variable here. So here's a function machine, and it's a machine we put real numbers into and we get real numbers out. Now, function machines are much good of thinking about individual functions, but they're great for thinking about functions in general. I love them. The three more specific ways of thinking about functions are the formula, which tells you what goes on inside the function machine, and the graph, which plots all the outputs. Now, to be a bit more precise, the graph in the xy plane consists of points xy, where y is f of x. In other words, it's an input-output pair. Now, mappings are just the same as functions, except that they can have more than one output. So here's a mapping we use every day of the week. X is mapped to plus or minus the square root of x. So that's got two outputs for positive x. Let's look at that in the three ways. So the function machine, I suppose we should call it a mapping machine, has a set of outputs rather than just one. The formula has options in it one way or another. And for the graph, well, some of the x values have more than one y value. So it's useful to flip between these three ways of thinking about functions when we introduce some new aspect of function theory, because they each bring their own insights. And what we're talking about today is the composition of functions. Now, function machines are really good at composition. So here are a couple of functions, g and f, and they're composed, which means we take an input, we feed it into g and get the output g of x, we feed that into f and get the output f of g of x. We can put a function machine box around the whole of that thing and call it fg so that its output is fg of x, which is just f of g of x. If we hide its innards, we see it's just another function machine, and if we put the innards back in again, we see that it's a function machine constructed out of two others. Composition using formulae is a bit more complicated. It's easy enough to write that gf of x is g of f of x, but when you have some real formulae to deal with, the formula gets pretty messy. And it's a whole lot worse if you look at graphs. So there's really no sensible way of working out what the graph of fg is going to look like by staring at the graph of f and the graph of g. And yet that's roughly what we're being asked to do. Well, this is exactly what we're being asked to do by Edexcel anyway, and the others are very similar. So we start with the function f, and we look at related functions. So we either take f and add or multiply by a constant, or we take its input and either add or multiply by a constant, and combination of these transformations. Well, I'm going to generalize these very slightly because I think the slightly more general transformations are easier to understand. So I'm going to use these two, which you'll spot are in fact combinations of the other ones, but I'm going to treat them as single transformations. And if we let g of x be mx plus c, then you see that this one is g of f of x, gf of x, and this one is f of g of x, which is fg of x. Now, to see what that means for the graphs and how they're transformed, I'm going to use ants. Yes, ants. So here we go. Here's the xy plane, and here's the graph of our function f. Now, we don't necessarily know the formula for f, just where the graph is. And here are some ants lined up on the x-axis, and their job is to line themselves up along the graph of gf. In other words, they have to go from x0 to x gf of x. Let's see how they do that. So we'll take the simplest example first, which is y equals f of x plus 1. So the ants don't know the formula for f, so the only thing they can do is sniff out the graph and go there. And now they have f of x as their y coordinates, so they just have to add 1 to it, and that takes the graph up. That's pretty much the same if we do 2f of x. So the ants sniff out the graph, and then they have to double their y coordinates, which stretches the graph out. And to be honest, it's really not much more complicated if we combine those. So 2f of x plus 1, they sniff out the value of f. Now they understand BIDMAS, so they know that what they have to do is first multiply their y coordinate by 2, stretching the graph out, and then add 1, shoving it up 1. Okay, now let's look at the next one. f of mx plus c. So now the ants have to go from x0 to x f g of x, which in this is going to be f mx plus c. So let's look at the first example again, which is y equals f of x plus 1. Now then, the ants don't know the formula for f, so the only way they're going to find out what f of x plus 1 is to go to x plus 1, which takes them right 1, then find f of x. Now, they've got their y coordinates correct, but they need to go back home because their x coordinate is incorrect. So they go back left, taking the graph with them, and that's why the graph goes left. F of 2x is very similar, of course, so now the ants stretch themselves out before finding the graph, and then have to go home, which involves shrinking the graph. Okay, now if we combine them, it is a bit more complicated. So they understand BIDMAS, so they know that they've got to go to 2x plus 1, and to do that they have to first of all stretch themselves out and then go right 1. Then they can find f of x, and that's got their y coordinates correct. So now they have to go home again, which means they have to undo the move they've just done. And the move they've just done is to stretch themselves out and then go right 1. So to undo that, they've got to undo those two steps in reverse order. So they've first got to go left 1, and they've then got to shrink. So the transformation that applies to the x-coordinate of a point on this graph is the inverse of g. Let's look at that algebraically. So when they move to their new coordinate x dash, 2x plus 1, g of x, they then have to go home. Now we can make x the subject of that equation and see that x is x dash minus 1 over 2, which is g to the minus 1 of x. So the transformation of the graph that the ants make when they move home is to apply the inverse of g to its x coordinates. Look at the function machine view of this. So here's our function machine. Let's start with a simple case first of all, gf of x. So the graph of f consists of points x, y, where x comes from here and y comes from here. The graph of gf consists of points x, y, where the x still comes from here, but now the y comes from here. So to transform the graph of f into the graph of gf, we take all these points and push their y coordinate through g. Now look at fg. So here the graph of f is over here this time. X comes from here and y comes from here. And the graph of fg consists of points x, y, where the y still comes from here, but now it's the x that moved and comes from here. So to transform this graph into this graph, we take these points x, y and push the x value backwards through g. That is to say, through the inverse of g. Now that's all very well, but what if g is not a one-to-one function and so doesn't have an inverse function? It just so happens that until 2017 there was just such a function in the syllabus, namely the modulus function. So let's have a look at that. The ants don't have any problem. So here's a simple case, mod of f of x. So the ants have to first of all sniff out the value of f, and then they have to take the modulus of their y value, which flips the graph up. So that's easy enough. Now let's look the other way around. So the only way the ants are going to find out what f of mod x is first of all to go to mod x, which means the ones that to the left of the y-axis have to reflect themselves in the y-axis, so that there are now two ants at each of these points. They then find f of x, and they then have to go home. Well, so there are two ants here. The one that started on the positive with the positive x coordinate sits still, and the other one has to reflect itself back in the y-axis, like this, taking a copy of the graph with it. Now let's just do that again and look at a particular point on the graph, say this one. So this point gets mapped to 2 points, itself and that one over there. So the transformation that's applied to the x-coordinate of points on the graph is still the inverse of g, but now it's the inverse as a mapping, not a function. Let's look at this again. So here we're transforming this graph to that graph, and we're moving this x backwards through g. But now there are two x's here that give rise to this function, this x here, and we need both of them. Only one-to-one functions have inverses that are functions, But all functions have inverses if we allow mappings. Let's look at that in the three ways. So for a function machine, if we have two inputs producing the same output, well, they're both outputs of the inverse mapping machine. For formulae, well, here's a simple quadratic formula. We can make x the subject of the equation, and this gives us an inverse mapping with options in it. The graph's rather pretty. So here's the graph of that same simple quadratic function. To find the graph of the inverse, we simply reflect it in the line y equals x. So here's the graph and the formula for the inverse of that simple quadratic function. And this is the graph of the inverse mapping of the modulus function that we just used. So each x is mapped to both x and minus x. So there we are. So the key points are to remember that the graph of f consists of the points x, f of x. To transform the graph of f into the graph of gf, we apply the function g to the y coordinates of these points. To transform the graph of f into the graph of fg, we apply the mapping inverse of g to the x coordinates of the points. Now in this video we've only used two very simple functions, g, mx plus c, and mod x. But in fact this formulation is completely general and will work with any g. And in my next video I shall explore function transformations a bit more and connect them to other parts of the syllabus.